All right, so in this video, we are going to read section 2.4, which is on continuity. And let's take a look at the learning objectives. Explain the three conditions for continuity at a point. This is important. Describe three kinds of discontinuities. Also want to know what those three kinds are. Define continuity on an interval. We'll talk about that. State the theorem for the limits of composite functions. And then finally, provide an example of the intermediate value theorem. So we'll talk about what that theorem is and then go over the example. All right, so as usual, we're just reading through the book. So let's go ahead and get started. Many functions have the property that their graphs can be traced with a pencil without lifting the pencil from the page. Such functions are called continuous. Other functions have points at which a break in the graph occurs, but satisfy this property over intervals contained in their domains. They are continuous on these intervals and are said to have a discontinuity at a point where a break occurs. We begin our investigation of continuity by exploring what it means for a function to have continuity at a point. Intuitively, a function is continuous at a particular point if there is no break in its graph at that point. Okay, so yeah, that last sentence there so far is, pretty good. A function is continuous at a particular point if there is no break in the graph at that point. So as you can see in this graph that's given below here in figure 2.32, if I just put a red dot here, like at this point, at that point there, it looks like the function is continuous because if you were to draw this function, you could draw that, through that point without lifting your pencil, right? Whereas at this point here, where x is equal to a, you would kind of have to draw your line, skip a little spot, and then there'd be an open circle there. We have discontinuity there. So we'll more formally define this, but that's the intuitive definition. So continuity at a point. Before we look at a formal definition of what it means for a function to be continuous at a point, let's consider various functions that fail to meet our intuitive notion of what it means to be continuous at a point. We then create a list of conditions that prevent such failures. So our first function of interest is shown in figure 2.32. We see that a graph of f of x has a hole at a. In fact, f of a is undefined. Right, so definitely if a function is not defined at that point, then it's going to have a discontinuity there. So at the very least, for f of x to be continuous at a, we need the following condition. F of a is defined, right? It should be defined there in order for it to be continuous there. Okay, let's continue reading. However, as we see in figure 2.33, this condition alone is insufficient to guarantee continuity at the point A. Although f of a is defined, the function has a gap at A. Let's take a look at figure 2.33. And you can see it down there. I'm trying to show the text at the same time. So we can see that this function that's pictured below is defined when x is equal to A. But you can still see that there's discontinuity. There's a gap there because you can't draw this graph without lifting your pencil, right? There's a gap. So we see that being defined at some value x equals a is not enough for continuity to be, for the function to be continuous at that point. In this example, the gap exists because the limit as x approaches a of f of x does not exist. And does not exist because, the limit from the left-hand side and the limit from the right-hand side are two different values, right? We can call this L1, we can call the other one L2. L1 and L2 are clearly not equal. And so since the one-sided limits are not equal, this double-sided limit does not exist. So we must add another condition for continuity at a, namely, the limit as x approaches a of f of x exists. So we have f of a is defined as our first condition. The limit as x approaches a of f of x must exist. But it turns out that this is still not enough for a function to be continuous. So let's continue reading. However, as we see in figure 2.34, these two conditions by themselves do not guarantee continuity at a point. The function in this figure satisfies both of our first two conditions, but is still not continuous at A. We must add a third condition to our list. And the third condition is that the limit as x approaches A of f of x is equal to f of A. So the limit, this is the limit that has to exist from condition 2, and the defined value at x equals A of the function f, not only must they both exist, but they both need to be equal to each other. Okay. Now we put our list of conditions together and form a definition for continuity at a point. So here's our definition. A function f of x is continuous at a point A if and only if the following three conditions are satisfied. F of A is defined. The limit as x approaches A of f of x exists. And then those two values from number 1 and number 2 are equal to each other. A function is discontinuous at a point if it fails to be continuous at A, right? So any of the, if any of this fails, then the function is not continuous at that value of x, A. Okay, so let's go ahead and look at the problem-solving strategy for determining continuity at a point. Check to see if f of A is defined. If f of A is undefined, we need go no further. The function is not continuous at A. If f of A is defined, then continue to step 2. And of course, if f of A is undefined, then we're already missing, the requirement number 1 in that list. So of course, if it's undefined, then you stop and it's not continuous. But if it is defined, well, then you need to check the next requirement, number 2. Compute the limit as x approaches A of f of x. In some cases, we may need to do this by first computing the left-handed limit and the right-handed limit. Okay, and of course, if these two are equal, then the limit exists. If these two are not equal, then the limit does not exist. So let's continue reading. If the limit as x approaches A of f of x does not exist, that is not a real number, then the function is not continuous at A, and the problem is solved. Right? Again, if the limit does not exist, then condition 2 is not satisfied. All three of the conditions need to be satisfied. So if the limit does not exist, then you can stop. And you can determine that the function is not continuous there. But again, well, what if the limit does exist? Then if the limit does exist, then you need to continue to step 3. Step 3 asks us to compare f of A and the limit as x approaches A of f of x. If these two values are not equal, then the function is not continuous at A. If the limit as x approaches A of f of x is equal to f of A, then the function is continuous at A. Right, so just a kind of a problem-solving strategy. The main one that we're looking for is that this is satisfied, because if this is satisfied, the third step here, if that third requirement is satisfied, then of course the limit must exist and be equal to f of A, right? But we're checking one at a time. Okay, the next 3 examples demonstrate how to apply this definition to determine whether a function is continuous at a given point. These examples illustrate situations in which each of the conditions for continuity in the definition succeed or fail. Okay, so let's go ahead and take a look at this one. Now here, you can actually see, just by, if we call this A, you can see that f of A is undefined. So this is not continuous. Or we could even say, so not continuous at x equals A. Or we can say discontinuous if you at x equals a. Now let's go ahead and, we can use this problem solving strategy here. Let's read the solution. Using the definition, determine whether the function f of x equals x squared minus 4 over x minus 2 is continuous at x equals 2. Justify the conclusion. And we've seen this function before. Let's begin by trying to calculate f of 2. We see that f of 2 is 0 over 0, which is undefined. Therefore, f of x equals, that function is discontinuous at 2 because f of 2 is undefined. Okay, nice. That was nice. If the first condition is not satisfied, you can stop there. Okay, let's continue. Well, we can see example 2.27, determining continuity at a point, condition 2. Using the definition, determine whether the function f of x equals, and we have negative x squared plus 4 for values of x less than or equal to 3, or 4x minus 8 if x is greater than 3. And we want to know whether or not this is continuous at x equals 3. Justify the conclusion. So let's start with step number 1, trying to calculate f of 3. Now we can calculate f of 3 because at an x value of 3, we're using this rule here, negative x squared plus 4. So all we have to do is plug in 3 into negative x squared plus 4. And we get an output value. We get an output value of negative 5. So f of 3 is defined, and it is defined to be negative 5. Okay, so then step 1 holds, right, or step 1 is satisfied. F of a is defined for a equals 3. Next, we should calculate the limit as x approaches 3 of f of x. To do this, we must compute the limit as x approaches 3 from the left-hand side of f of x, and the limit as x approaches 3 from the right-hand side of f of x. So if we are computing from the left-hand side, as we talked about before, then keep in mind that the limit as x approaches 3 from the left-hand side, it means that you are looking at values approaching 3, but from the left-hand side, so values less than 3. And if we are looking at values less than 3, approaching 3, then we are using this top rule here. And so we can use direct substitution to figure out what we would get as our limit for x approaching 3 from the left-hand side. We plug in our 3, and the limit is negative 5. Okay. Okay, nice. What about from the right-hand side? Again, so for the limit as x approaches 3 from the right-hand side, we are looking at values of x that are less, not less than, greater than, right? Because we're from the right-hand side, greater than 3. And so for values of x greater than 3, we are looking at the other piece of this piecewise function. And we are approaching 3 from the right-hand side. So we can use direct substitution here, plug in our 3, and we see that we get an output value of 4. So notice that the limit as x approaches 3 from the left of f of x is not equal to the limit as x approaches 3 from the right of f of x. Since these two are not equal, we have said in a previous section that this implies, or this is equivalent to, the limit as x approaches 3, this is the double-sided limit of f of x, does not exist. So since this does not exist, requirement 2 is not satisfied. Thus, f of x is not continuous at 3. And then the graph shows this. You can see there's a gigantic gap. Right from the left-hand side, we are approaching negative value. It turns out to be negative 5. We computed. And then from the right-hand side, we're approaching some y value, and it turns out that this is a positive 4. This is a value of positive 4. Okay, so we fail to have a limit at x equals 3, even though the function is defined there. the limit does not exist. What about this one here? Example 2.28, determining continuity at a point. And this is condition 3. Using the definition, determine whether the function f of x equals sine x over x if x is not equal to 0, and 1 if x is equal to 0 is continuous at x equals 0. So we want to determine whether or not this function is continuous at x equals 0. So let's look at condition 1. Condition 1 is to check that f of x, the function, is defined for that specific value, x equals 0. And according to this the way that this function is defined, at x equals 0, the function is defined to be 1. So the function is defined at x equals 0. Next, we should check the limit. The limit as x approaches 0 of f of x is the limit as x approaches 0 of sine x over x. And this can be shown to be 1. It's actually shown in the previous section. So then we compare these two values, f of 0 compared to the limit as x approaches 1. And this should be limit as x approaches 0, a little typo there, of f of x. And since both of these are equal to 1, then that means that they are equal to each other. Since all three conditions of the definition of continuity are satisfied, f of x is continuous at x equals 0. And just to quickly check the limit as x approaches 0 of sine x over x, let's just check this graphically. Sine x over x. And you can see, even though this function is not defined when x is equal to 0, you can see it's undefined there, 0 undefined. But we can, make a piecewise function where if x is equal to 0, then we use the rule that x is, or that the y value, the function value is 1. And therefore, the limit does exist. It is equal to 1, as you saw from the graph. And the function value is defined to be 1. All right, so very nice. You can try 2.21 if you like. So by applying the definition of continuity and previously established theorems concerning the evaluation of limits, we can state the following theorem. Theorem 2.8, continuity of polynomials and rational functions. So there was a theorem, I believe it was theorem 2.6 that we talked about before, that said that basically if you wanted to calculate the limit as x approaches a for some polynomial p of x, that was just equal to p of a. And notice this is the exact requirement for a function to be continuous. And so that's what this theorem says. Polynomials are continuous at every point in their domain. And theorem 2.6 also talked about rational functions. The same basically held with rational functions. Oh, and it's right here. You can see it right there. This was the statement of theorem 2.6. That was part of it, and here's the other part. It turns out that rational functions are also continuous at every point in their domain. So previously, for the proof, we can just read it really quickly since it's 2 lines. Previously, we showed that if p of x and q of x are polynomials, the limit as x approaches a of p of x is p of a for every polynomial p of x, and the limit as x approaches a of p of x over q of x is equal to p of a over q of a as long as q of a is not equal to 0. Therefore, polynomials and rational functions are continuous on their domains. All right, so very nice. That's kind of cool. We didn't have that definition before, so we couldn't really state that before, but there we go. That's the statement. So we now apply continuity of polynomials and rational functions to determine the points at which a given rational function is continuous. So example 2.29, for what values of x is f of x equals x plus 1 over x minus 5 continuous? And we said that it is continuous at every point in its domain. So the domain is just going to exclude the values where x minus 5 is equal to 0. And you could pretty much see that without even writing it down. But at x equals 5, this function f of x is discontinuous. So the domain of f is equal to, basically all real numbers except for 5. So the rational function f of x is continuous for every value except x equals 5. Yeah, very nice. You should be able to do 2.22, example 2.22 here in your head, and it should take you about, 5 seconds if you understand what theorem 2.8 is saying. If you don't understand or you don't know the answer to 2.22, you can talk to me during my office hours. Types of discontinuities. So as we have seen in example 2.26 and example 2.27, discontinuities take on several different appearances. We classify the types of discontinuities we have seen thus far as removable discontinuities, infinite discontinuities, or jump discontinuities. So intuitively, a removable discontinuity is a discontinuity for which there is a hole in the graph. Okay, so here is a removable discontinuity. We've seen functions like this before. We saw an example just a moment ago. A jump discontinuity, it's kind of in the name, is a non-infinite discontinuity for which the sections of the function do not meet up. So there is a bit of a jump, right, in between the sections of the function. And yeah, they give us more precise definitions coming up ahead, because you could say, well, what about this one here? These pieces of the function don't meet up. So let's continue here. An infinite discontinuity is a discontinuity located at a vertical asymptote. Figure 2.37 illustrates the differences in these types of discontinuities. Although these terms provide a handy way of describing the 3 common types of discontinuities, keep in mind that not all discontinuities fit neatly into these categories. Yes, there are more complicated functions out there, but these are the main ones that we'll look at in this class. These 3 discontinuities are formally defined as follows. So let's just go over this definition here quickly. If f of x is discontinuous at a, then f has a removable discontinuity if at a, if the limit as x approaches a of f of x exists. Note, when we state that the limit as x approaches a of f of x exists, we mean that the limit is equal to L, where L is a real number, right? We're not talking about an infinite limit, but a real number limit. Okay, and so of course that must mean if this limit exists, so just to expand on this a little bit, then the limit as x approaches a of f of x, this exists. It is not going to be equal to f of a for some reason. Either f of a is not defined, or f of a is some other value, like you see in this picture here. F of a is, or f is defined at a, but it is not equal to the limit for some reason. Okay. If this dot was completely missing, it would still be a removable discontinuity. The limit exists, but the function for some reason is not defined to be equal to that limit at a. Next. F has a jump discontinuity at a if the limit as x approaches a from the left and the limit as x approaches a from the right both exist, but they are not equal to each other. Okay. When we state that the limit as x approaches a of f of x and the limit from the right both exist, we mean that both are real valued and that neither take on the values plus or minus infinity. Okay. And then finally, the third one, f has an infinite discontinuity at a if the limit from the left is plus or minus infinity, one of those two, or the limit from the right is plus or minus infinity, okay, as you can see in the picture example. All right, very nice. So let's go ahead and take a look at the next example, example 2.30. In example 2.26, we showed that f of x equals x squared minus 4 over x minus 2 is discontinuous at x equals 2. Okay. Classify this discontinuity as removable, jump, or infinite. Solution. To classify this discontinuity at x equals 2, we must evaluate the limit as x approaches 2 of f of x, and we did this one in class. You can use algebraic reduction for this. So the limit as x approaches 2 of f of x. Let's go ahead and try to, well, they tried to plug in 2 earlier and you got 0 over 0. So then we can try to factor the numerator. The numerator is nice and it factors into a difference of squares. Since it's a difference of squares, it factors to x minus 2 times x plus 2. Then we can essentially cancel these two factors, and the limit as x approaches 2 of x plus 2 is 4. So we know that f is discontinuous at 2. The limit does exist. So then f has a removable discontinuity at x equals 2. Okay. Remember, because the three options are that if the limit exists, then we have a removable discontinuity, assuming the function is discontinuous there. If the limit does not exist, then we may have a jump discontinuity, assuming that both of the limits from the left and the right exist independently but are not equal to each other. And then, of course, we have the infinite discontinuity, which occurs when the limit from the left or the right is either positive infinity or negative infinity. So let's try to classify the next one. In example 2.27, we showed that the function f of x is discontinuous at x equals 3. Classify this discontinuity as removable, jump, or infinite. We already saw the picture. So if you remember what the picture looked like, then you know that this is a jump discontinuity. But how would we actually show that, algebraically? Well, we're going to show that the limit from the left exists and the limit from the right exists, but the double-sided limit does not exist. And therefore, there must be a jump. Oops, where were we? And so that's exactly what is done here. Solution. Earlier, we showed that f is discontinuous at x equals 3 because the limit as x approaches 3 of f of x does not exist. However, since the limit from the left is -5 and the limit from the right is +4, both exist, we conclude that the function has a jump discontinuity at x equals 3. All right, that's what we expected. And then finally, the last one here, determine whether f of x equals x plus 2 over x plus 1 is continuous at x equals -1. If the function is discontinuous at -1, classify the discontinuity as removable, jump, or infinite. So we tried to find, the function value f of -1, and we see that it is undefined. Since it is undefined, if you remember the definition of continuity, the definition of continuity had 3 requirements. We had to meet all 3 of these in order for, f to be continuous. F is continuous if, step 1 was, and we should say continuous at A. So let me. At A, if f of A is defined. This was just the first requirement. Well, we just saw that f of -1 is undefined for this function. Therefore, this function f cannot be continuous at -1. So we know the function is not continuous. So we want to now classify the discontinuity. So continuing on here, to determine the type of discontinuity, we must determine the limit at -1. And we see that the limit as x approaches -1 from the left is -infinity. Now, to see this, we could take a look at a table of values, right? That's one way to do it. And then the limit from the right-hand side is positive infinity. And so therefore the function has an infinite discontinuity at -1. Okay. All right, very nice. This is page 186. We will come back here, yep. So let's go ahead and take a look at the next part here. So continuity over an interval. We talked about, whether a function is continuous or not at a single point at a value of x equal to a, but what about over an entire interval? Now that we have explored the concept of continuity at a point, we extend the idea to continuity over an interval. As we develop this idea for different types of intervals, it may be useful to keep in mind the intuitive idea that a function is continuous over an interval if we can use a pencil to trace the function between any 2 points in the interval without lifting the pencil from the paper. In preparation for defining continuity on an interval, we begin by looking at the definition of what it means for a function to be continuous from the right at a point and continuous from the left at a point. Okay, so let's go ahead and take a look at that definition. Continuity from the right and from the left. So a function f of x is said to be continuous from the right if, notice this is very similar to the condition for continuity from before. So continuity from the right at a, if the limit as x approaches a from the right is equal to f of a. Okay, so the only thing is we're looking at the limit from the right only. A function f of x is said to be continuous from the left at a if the limit as x approaches a of f of x is equal to f of a, but the limit that we're looking at is from the left. Okay. All right, so we'll see why we need this definition in just a moment. So let's go ahead and take a look at, let's continue reading. A function is continuous over an open interval. Let's see here. Sorry about that, my computer did something funny. A function is continuous over an open interval if it is continuous at every point in the interval. A function f of x is continuous over a closed interval of the form a, b with square brackets if it is continuous at every point in a, b, open interval, and is continuous from the right at a, and is continuous from the left at b. Analogously, a function f of x is continuous over an interval of the form a, b, where a is not included and b is, if it is continuous over the open interval a, b, and is continuous from the left at b. And it makes sense if you're looking at an interval of this form, a, b, notice that b is included in the interval. So b is included in the interval. We want to be continuous at b. So how do we get continuity at b? It could only be from the left-hand side. So that's why we are looking at continuity from the left at that specific point b. For any other value in the interval, we could be continuous from both sides. So we just say we're continuous on the open interval, but at b, specifically, we only need to be continuous from the left because we can't be continuous from the right because the function might not even be defined to the right of b. Continuity over other types of intervals are defined in a similar fashion. So requiring that the limit as x approaches a from the right of f of x equals to f of a, and the limit as x approaches b from the left of f of x is equal to f of b ensures that we can trace the graph of the function from the point A f of A to the point B f of B without lifting the pencil. If, for example, the limit as x approaches A from the right of f of x is not equal to f of A, we would need to lift our pencil to jump from f of A to the graph of the rest of the function over A to B, where A is included and A is not included and B is. So let's take an example, because that could be, if it's hard to understand in those general terms there, we can look at a specific example and, maybe we can even graph this. Okay, so state the intervals over which the function f of x is continuous. So solution, since f of x is equal to x minus 1 over x squared plus 2x is a rational function, it is continuous at every point in its domain. That was the theorem that we saw earlier. The domain of this function is the set, and let's just take a close look at this. So x squared plus 2x, that's the denominator. This is equal to, if we factor out an x, we can get x times x plus 2. And we see that this denominator is equal to 0 when x is equal to 0 or when x is equal to -2. So we will exclude both of those values from the domain. So the domain of f of x is this set here, all real numbers except for -2 and 0. Thus, f of x is continuous over each of the intervals, and those each individual intervals is where f is continuous. Okay, nothing too new there. Let's take a look at the next one. Here's a good example. And let's graph this one. F of x equals the square root of 4 minus x squared. So the square root of 4 minus x squared. And so you can take a look at this graph here and notice that we could only be continuous, let's say, at the point over here, -2, 0. At the point where x is equal to -2, we could only be continuous from the right, because this function does not exist, further to the left of -2. So the x values can approach -2 from the right. And so we could have continuity from the right, but not from the left. And then the opposite is true from the other side. We can have continuity from the left towards the rightmost point of 2, 0. So let's take a look here. Solution, it says from the limit laws, we know that the limit as x approaches a of the square root of 4 minus x squared is equal to the square root of 4 minus a squared for all values in the interval, the open interval from -2 to 2. We also know that, so what is the right side limit? The limit as x approaches -2 from the right is equal to 0. It definitely exists because we know it's equal to 0. We saw it from the graph. And the limit as x approaches 2 from the left, this was the other side, this is also equal to 0. And therefore it exists. Therefore, f of x is continuous over the interval from -2 to 2 inclusive, right? That's a closed interval from -2 to 2. Okay, so let's just kind of summarize here what we said. And the first part where the limit as x approaches a of the square root of 4 minus x squared, I don't know if we want to see all that again from when we did this before, but we said we could say, okay, using the limit laws, this is equal to the limit as x approaches a of 4 minus x squared. And then we could factor out that square root or apply the square root to the limit. And then since the limit is a limit of a polynomial, now that limit is going to be 4 minus a squared. And then we apply that square root to the limit. And so that's exactly what they said in this statement here. And notice that this is exactly equal to just f of a. So the limit as x approaches a of f of x, well, the limit as x approaches a of f of x is equal to f of a. And that is the condition that needs to hold. This is the third condition that needs to hold for continuity. So we have continuity for all of the numbers, all of the x values from -2 to +2. But what about at the, let's say at the leftmost value? What about at x equals -2? Whenever we're looking for at x equals -2, since it is in the interval from -2 to +2, notice that we can only have continuity from the right, right? Because it's at the leftmost value in an interval. So then what we need to hold is that the limit as x approaches -2 of our function f of x is equal to f of -2. Now, what is f of -2? That's easy to compute. F of -2 is equal to the square root of 4 minus -2 squared. And this is the square root of 4 minus 4. This is equal to the square root of 0, which is 0. Now, the limit, so we know that the right-hand side of this equation here is 0. Well, what about the left-hand side of this limit? Or the left-hand side of this equation? Well, we can say from the graph we saw that the limit is 0. This function is definitely defined when x is equal to -2. And so our limit is 0. Since both of these are equal, that condition here is satisfied, and therefore the function is continuous from the right at x equals -2. Okay, and then a similar argument holds for x equals +2. And then so now that we have continuity from -2 to +2 on the open interval from -2 to +2, we have continuity at x equals -2 because this holds here. And then a similar argument can show continuity at x equals +2. Putting all of this together, we get continuity over the closed interval -2 to +2. All right. Next, we have the composite function theorem. So the composite function theorem allows us to expand our ability to compute limits. In particular, this theorem ultimately allows us to demonstrate that trigonometric functions are continuous over their domains. So let's go ahead and see how we would do that. So theorem 2.9, the composite function theorem. What does it say? If f of x is continuous at L and the limit as x approaches a of g of x is equal to L, then the limit as x approaches a of f of g of x is equal to, notice that f is then applied to the limit as x approaches a of g of x, and that is equal to f of L. All right, so let's go ahead and take a look at how this is used here. So continuing, it says, before we move on to example 2.35, recall earlier in the section on limit laws, we showed that the limit as x approaches 0 of the cosine of x was equal to 1, which is equal to the cosine of 0. So the limit as x approaches 0 of the cosine of x, this can be seen pretty easily in a graph.
the limit as x approaches, and let me just graph cosine here. Cosine starts up at 1 and it goes like this. And then if you go the other way, it goes something like that. And so we can see that the limit as x approaches 0, is that y value, which is 1, which is the cosine of 0. Consequently, we know that f of x equals cosine of x is continuous at 0. In example 2.35, we see how to combine this result with the composite function theorem. All right. So let's take a look at this problem, and then we'll kind of break it down. The limit of a composite cosine function. So evaluate the limit as x approaches pi over 2 of the cosine of x minus pi over 2. So solution, the given function is a composite of cosine of x and x minus pi over 2. Since the limit as x approaches pi over 2 of x minus pi over 2 is 0, and cosine of x is continuous at 0, we may apply the composite function theorem, and thus the limit as x approaches pi over 2 of the cosine of x minus pi over 2 is equal to the cosine of the limit as x approaches pi over 2 of x minus pi over 2, which is equal to the cosine of 0, which is equal to 1. Okay, so let's go ahead and break some of that down here. So let's write down our composite function theorem one more time. So f of x is continuous at L. So that's one thing that we need. And the limit as x approaches a of g of x is equal to L. If both of these conditions here, or if both of these things are met, then the limit as x approaches a of f of g of x is, you can compute it by applying f to the limit as x approaches a of g of x. And of course, we know that the limit is equal to the limit inside of those parentheses, that last set of parentheses is L, and we have f applied to that. Okay, so let's try to now see this applied to the problem. So what is our function f? Okay, so let's take a look here. So the limit that we want to compute is the limit as x approaches pi over 2. All right. So let's take a look at, so this composite function theorem helps us to compute the limit of a composite function, right? There is a function f that's being applied to another function g of x. And then we're trying to find the limit of that. So what we can do is we can look at the problem that we're given and notice that we have a function cosine of x that is applied to another function, which we could call x minus pi over 2. And then we are trying to find the limit of that, right? So in this case, f, it looks like f of x is cosine of x, okay? G of x is equal to what? The inner function we said is x minus pi over 2. And so we need that the limit as x approaches a, here we are taking the limit as x approaches pi over 2. We need the limit as x approaches pi over 2 of this function g of x, which we just said is x minus pi over 2, to be equal to some value L where f is continuous at L. So what is this limit here? Since this is x minus pi over 2 is a polynomial, we can just plug right in. We can plug in pi over 2 for x, and we get 0. Now, f of x is cosine x, and is it continuous at 0? The answer is yes. I mean, that's what was talked about, here, right before the problem started. So f of x is cosine of x, and it is continuous at 0. So then both of the conditions are satisfied. We have this limit, and then f is continuous at that limit. So what the composite function theorem tells us is that the limit as x approaches pi over 2 of our function f of x applied to x minus pi over 2 is equal to my function f, which is the cosine, applied to the limit as x approaches pi over 2 of my function g of x, which is x minus pi over 2. Now, we already took that limit, and we said that the limit was 0. And so this works out to just be the cosine of 0, which is equal to 1. So this, somewhat complicated limit can be broken down into a simpler limit, and then we apply a function to it. And so we got our answer of 1. So let's just go through the solution one more time. It says the given function is a composite of cosine of x, which is f, and x minus 2, which we call g. Since the limit as x approaches pi over 2 of g is equal to 0, well, we need to check to make sure f is continuous at that limit of 0. And cosine of x is continuous at 0, so it is. We may apply the composite function theorem, and thus, exactly what we just said, the limit is equal to 1. Okay. The proof of the next theorem uses the composite function theorem, as well as the continuity of f of x equals sine x and g of x equals cosine x at the point 0 to show that trigonometric functions are continuous over their entire domains. So theorem 2.10, continuity of trigonometric functions. And then basically just says trigonometric functions are continuous over their entire domains. Now, I'm not going to go over this proof in detail. So yeah, we'll go ahead and skip the proof for now. If you want to see the proof or you want to talk about the proof, feel free to visit me during the office hours, and we can go over it. But it's not going to be needed for us. Okay, as you can see, the composite function theorem is invaluable in demonstrating the continuity of trigonometric functions. As we continue our study of calculus, we revisit this theorem many times. So yes, it definitely is important to know this statement. So trigonometric functions are continuous over their entire domains. And you can tell that by looking at the let's say the sine function, you can probably tell that it's continuous. But this proof here actually proves that we prove continuity at every single point in the domain of each of these trig functions. So it is an interesting proof, but we'll skip it for now. Finally, we are at the intermediate value theorem. This is also a very important theorem. It's really important. Functions that are continuous over intervals of the form, the closed interval from a to b, where a and b are real numbers, exhibit many useful properties. Throughout our study of calculus, we will encounter many powerful theorems concerning such functions. The first of these theorems is the intermediate value theorem. So what does the intermediate value theorem say? Let's take a look. Theorem 2.11. The intermediate value theorem. let f be continuous over a closed bounded interval AB if z is any real number between f of a and f of b, then there is a number c in the interval from a to b satisfying f of c is equal to z. So let's kind of break this down. There's a nice picture here for us to use. And essentially what the intermediate value theorem says is, okay, we're at an interval from a to b, right? You can see that in the drawing below. I'm going to draw all over it. So we're in the interval from a to b. And so we're saying that f is a continuous function on the closed and bounded interval from a to b. Okay, so that means that wherever a is, and I'm going to use maybe red here just to make it stand out a little bit more. So here's my point f of a, and here a f of a, and here's my point b f of b. And so no matter how I draw this function, I can draw, I can draw various different shapes. Oops, that's not a function. Let's draw something like this. Something like this. Or it doesn't matter. I can ask anybody in this class here to draw a picture, a continuous graph from point A f of a to point B f of b. Doesn't matter how I draw it, but what the intermediate value theorem says that is, okay, well, obviously there is for the value a and the x value of b, there is an output value. So for a, I'll highlight it in yellow, there is an output value of f of a. For b, there is an output value of f of b. And so what the intermediate value theorem says is that if z is any real number between f of a and f of b, and here it just randomly got chosen to be right there. So any value between f of a and f of b, so this is a y value, then basically what it's saying is, as you move to the side here, there has to be a point somewhere on this graph in the interval from a to b where the function f has the value z. Okay. So now, does this make sense? Well, the simplest case here is in my blue graph, the one that I drew, and maybe I can kind of outline it a little bit more, right? And so this is the simplest case here probably that we can look at. If you're at a height f of a, and you're going to continuously rise to a height of f of b, then what the intermediate value theorem says is, well, for any number between f of a and f of b, your function must cross that height, right? Your function is going to end up at a height of z at some point. And you could say, well, yeah, that's obvious. I mean, hopefully, obvious in the sense, if you're rising from a height of f of a to a height of f of b, well, yeah, and you have to do it without lifting your pencil, you're going to go through every single y value all the way up to f of b. So if z is any real number between f of a and f of b, then there has to exist a value c in the closed interval from a to b such that f of c is z. Okay, and you can see that that's actually true with any of the graphs that I made here, right? You can draw this graph as long as it's continuous. Let's take the purple one, for example. Yeah, and it has a couple loops, but notice that at this point here, I'll mark it in big in purple, at this point here as well, and at this point here as well. It may even occur more than one time where, C1 occurs where f of C1 we can see is z from the picture. If I call this, C2, you can see f of C2 is also z, and f of, if we call this C3, it occurs multiple times in this case. The intermediate value theorem only says it needs to occur, once. It only needs to occur once, but it will definitely occur at least once. Same thing with my red graph here. In this red graph, I start at a height of f of a. If I'm going to somehow make it to a height of f of b, and oops, I don't know why that happened. If I make it somehow to f of b, somewhere in this interval, when I move from left to right, I'm going to have to cross this value of z, and it's going to have to occur for some value c in the interval from a to b. Okay, so that's the intermediate value theorem. So let's go ahead and take a look at an example. So here is, there's a couple examples here. Yeah. So let's take a look at it before we end this video. So first of all, here, this function f of x equals x minus cosine of x. We want to show that this function has at least one zero. Okay. So let's read the solution and we'll kind of try to break it down a little bit. Since f of x equals x minus cosine of x, we know that this function is continuous over all real numbers. And it says it is continuous over any closed interval of the form from a to b. Okay, if it's continuous everywhere, it must be continuous, on any closed interval. If you can find an interval from a to b such that f of a and f of b have opposite signs, meaning one is positive and one is negative, then you can use the intermediate value theorem to conclude that there must be a real number c in the open interval from a to b that satisfies f of c is equal to 0. So note that f of 0, if we take a look at f of 0, and I'll actually write it down and just do the little calculation, f of 0 is equal to x minus cosine of x, so 0 minus the cosine of 0. This is equal to 0 minus 1, which is negative 1. And then, so we have a negative value here. Now we just want to find one more x value where the function produces a positive value. So f of pi over 2 is the one that they chose. There are many values that you could choose for this. So pi over 2 minus the cosine of pi over 2. Pi over 2 minus the cosine of pi over 2. Cosine of pi over 2 is equal to 0. So this is pi over 2, which is a positive number. It is greater than 0, right? So we had negative 1 as one of our output values, which was less than 0, and then pi over 2, which is larger than 0. Now let's go ahead and draw a graph, because this is probably where we'll see most of the understanding here, or where we'll get most of the understanding. So here is my x-axis, here is my y-axis. I will graph my points. They are 0, negative 1. So I will do 0, negative 1. And then pi over 2, I forget exactly what that is. That's roughly, 3 divided by 2. So 1.5 roughly. So 1, 2, negative 1. And I will do 1, 2. So one of my points, I'm going to graph it in red, is 0, negative 1. And the other point is pi over 2, comma pi over 2. So I'm just going to use 1.5, comma 1.5 as my approximation. So we found these 2 points. Now notice the intermediate value theorem says that for any value between negative 1 and pi over 2, for any value between negative 1 and positive pi over 2, we basically must attain that value at some point on the interval from, this interval goes from 0 to pi over 2. So there must be some value c in the interval from 0 to pi over 2 such that f of c is equal to 0. Okay. And you can see, okay, if you're going to draw a continuous function, well, yeah, of course you're going to have to cross a height of 0, right? A height of 0 is this x-axis here. And you can see that that red curve, you know, I dare you to try to draw a continuous curve from one of those red points to the other and not cross the x-axis. You know, you can't do it because the intermediate value theorem says that you have to. Okay, so the last statement here says, using the intermediate value theorem, we can see that there must be a real number c in 0 to pi over 2 that satisfies f of c equals 0. Therefore, f of x has at least one 0. X minus cosine of x, and I'm just curious to see what this function looks like. So we don't even know what the entire thing looks like, but we know that it must cross the x-axis at some point there. And here is the function. You know, so there we have our point. You know, 0, -1, and then whatever pi over 2 is. I don't remember what pi over 2 is, but you know, you can see it crosses the x-axis right there. All right, very good. Almost done. All right. So when can you apply the intermediate value theorem? If f of x is continuous over the closed interval from 0 to 2, f of 0 is greater than 0, f of 2 is greater than 0, can we use the intermediate value theorem to conclude that f of x has no zeros in the interval from 0 to 2? And so, you know, we can graph this and kind of show that the intermediate value theorem actually does not really say much about this function here. What it does say is, okay, so there's an interval from 0 to 2, 0 to 2. And we're told that f of 0 is a positive number. So f of 0, you know, is, let's just say it's 1 for some reason, right? Any positive number, you can choose any positive number. And f of 2 is, let's say 3, another positive number, some other positive number. Can we use the intermediate value theorem to conclude that f of x has no zeros in the interval from 0 to 2? Well, the continuous function could be like this, and it might have no zeros in that interval. But the intermediate value theorem doesn't say that it will have no zeros, because the function could also be like this and actually have zeros. What the intermediate value theorem says is that every value between the beginning y value, which in this case is 1, and the ending y value, which in this case is 3, every y value between 1 and 3 will be attained by the function. And you can see that the function does attain these values here. Actually, we can even just shorten it by saying, look, it attains all of the values between 1 and 3 on this part right there. And maybe I'll use a different color on this part right there. That's what the intermediate value theorem says, is somewhere in this interval from 0 to 2, the function will attain, you know, each individual value between f of a and f of b. Okay, so the solution? No, the intermediate value theorem only allows us to conclude that we can find a value between f of 0 and f of 2. It doesn't allow us to conclude that we can't find other values. To see this more clearly, consider the function f of x equals x minus 1 squared, which is another counterexample to this. And we could graph it maybe really quick here just to take a look at their example. X minus 1 squared, that's going to be, and let's see here. Yeah, that's going to be, it's a parabola, right? That looks something like this. And we can see it definitely is defined over the interval from, let's call this from A to B, where A is 0, B is 2. And we can see that f of A, which is really f of 0 in this case, is equal to 1, which is larger than 0. f of b, which is f of 2, is equal to 1 as well, which is larger than 0. But you can see that it has a 0, an x-intercept in that interval. So the intermediate value theorem doesn't say that we won't have zeros in that interval. Okay, so, and then finally, the last example, 2.38. When can you apply the intermediate value theorem? Well, for f of x equals 1 over x. So let's take a look here. This is an interesting one as well. There's a lot of little intricacies that we will talk about in class, but for the intermediate value theorem. And so for the function f of x equals 1 over x, well, let's see, at -1, the function value here is -1. And at +1, the function value is +1. So does the intermediate value theorem say that we are guaranteed to have a 0 on the interval from -1 to +1? So let's read the problem one more time. For f of x equals 1 over x, f of -1 is -1, which is less than 0, and f of +1 is +1, which is greater than 0. So since can we conclude that f of x has a 0 in the interval from -1 to +1? The answer is no. You can see in the solution, because the function is not continuous over the interval. If the function was continuous, then yes, the intermediate value theorem would guarantee that you have to cross the x-axis there. But it turns out that the function 1 over x, if you know this function, I'm sure you've seen it before, it looks like this. And it has an infinite discontinuity in this interval. So since there is a discontinuity on the interval that you're talking about from -1 to +1, well, then the intermediate value theorem doesn't say anything about this function, because if you look closely at the intermediate value theorem, it says let f be a continuous function over a closed and bounded interval, let's say from -1 to 1. Well, f is not a continuous function on that interval for this problem here. So then the intermediate value theorem doesn't apply. You can't apply it, to guarantee. Notice, yeah, this function here does not have a 0 actually on that interval, but that's because there's discontinuity, right? We can't apply the intermediate value theorem. So it's a cool, very cool statement there, but it has a lot of intricacies to it, and that's why there were 3 examples involving it. So we'll stop there. So this video is not too terribly long. Yeah. All right. Very good.